All right, so now we're going to look at Taylor and Maclaurin series. This is just my opinion. It might not be the same for you, but I believe this is the most challenging concept in Calculus 2. And you may think so too if you know what this is, which hopefully you do because this is a review. But why I say that is not that really it's hard to understand what these series are. It's just when you're creating these series, as you may remember, you need to find like patterns. And that can be really hard to do. But we'll talk about that. But first of all, as a review, what oh, sorry about that. This dumb thing. I was trying to turn on the laser. But anyways, uh we'll look at that in a second, what that clip is. So what are these? These are how we can represent functions as series. So we just talked about power series, and this is a sort of way that we're able to actually do that. Like say, okay, here's a function, because now we've learned about series. Now we're saying, okay, how can we relate these to these functions that we've known? And ultimately, what a Maclaurin series is actually a type of Taylor series. It's just a type of Taylor series where the center is zero. So this value right here, that's a, is going to be zero. So it's really just x to the n. That's the only difference between the two. So basically, a Maclaurin is a type of Taylor series. But what do these do? Well, if you remember, let's say we're trying to approximate a point, we can say, all right, let's find the slope here. That's first derivative. Let's find uh, the slope of that slope, second derivative. And you can actually just go infinitely. And if you add up all those derivatives, we're going to say, all right, that's exactly what the series is for the function. If we do that, we're like first derivative, second derivative, like all the way to infinity derivatives. That's what a Taylor series basically is doing. Um, I think sometimes professors don't really explain that, but that's basically what we're doing. We're just like finding the slope of the slope of the slope, like that kind of. Essentially, that's what we're doing, to find the series of the function. So, like I said, the difference is that Taylor series is not going to necessarily be centered at zero. It could be something else, like centered at two, it would be x minus two. Centered at negative one, it would be x plus one. It's like that, like just like how when we find the x-intercepts, it's kind of opposite sign because it's really just the a. We don't think about that. So if a is negative one, it will be x plus one, right? So that thing is not hard to find, but the issue is that we need to find Cn to represent this. So this, like, is so easy to do. If you're told find the Taylor series at x equals 2, you just would say, okay, this part's just x minus 2 to the n. But the trick is to find this part, Cn. And Cn is equivalent to it's not f to the n, it's actually, what that means is the nth derivative at a divided by n factorial. Well, if you're like me, I don't want that. I'm like, what the heck does that mean? Well, there's a way to derive this. I'm not going to go into that because, in my opinion, it doesn't really matter. But you just need to memorize this. N factorial, okay, that's not hard to do. That's always going to be what that is. But the thing that will change from problem to problem is the nth derivative of a. And what this means, this little piece right here, is saying, what the heck is the pattern of the derivatives? It's almost like how we found patterns to of in the sequence of terms to create the sequence. Now we're like, okay, we're going to take a few derivatives of the function and say, what are the patterns here? And whatever we find out, we'll replace for that. And that will tell us Taylor series. But as I mentioned, this is actually pretty hard to do sometimes. But here's what you do. You first just take a few derivatives. Usually four is enough. So let's say our function was, I don't know, e to the x. That's like one of the easiest ones. You'd say, okay, first derivative, e to the x. Second derivative, e to the x. E to the x, all of them are that, right? So that's you do something like that, and I guess that's not really a good example. There will be ones where it changes. So, maybe it was like square root of x plus one or something. I don't know. Just take a few derivatives of that. Now, here's the thing. You, when you're taking these derivatives, if you have like power rule that you're doing, don't multiply things together. Don't simplify anything. So for example, let's say you're doing x squared. All right, we're doing the derivatives. Okay, 2x, right? Well, actually, that's a bad example. Let's start at let's say it was x to the fourth. Sorry. Then the first derivative, 4x cubed. But then for the next one, you wouldn't want to say 12x squared, right? Say 4 times 3x squared. You would want to keep leaving it to the side because if you multiply everything together, it's so hard to see what the pattern is. So that's what this audio comes in. You'll kind of feel like this. It will be like, okay, let me rip this test into pieces and throw it at my professor. You don't want that to happen, right? This is hard to do, but that's what you do. And we'll look at some examples. So remember, watch that example video. I'll try to get that out soon. Uh, it makes it way harder if you don't do that. That's that's it though. Then when you find the pattern, you might just be like, the way that you have to do this, well, yeah, so you first find the derivatives, like I said, find 4 derivatives. Usually that's enough. Then not only do that, you find with those derivatives the value um that it says. So whatever this A was, like centered at 2, if it said that, you'd plug in 2 to all of those derivatives and see what numbers you get. Now, the thing about that is that you don't always have to do that. That's why this is a little tricky of a concept. Like sometimes you might not need to do that. You might already see the pattern with the derivatives. But if you can't, it might be helpful to instead plug it into um, the derivatives. Plug in your A value to all the derivatives and see if that's another way you can see a pattern. Now, what you do is you basically, how do you turn the what pattern you see into this is the same as we've done before. You relate everything to n, so you'll say, well, this part is always one more than n. Okay, we'll say n plus one, things like that. Or this part always is n factorial, so you'll say, okay, n factorial. And that'll make more sense when we look at examples, but that's how you do it, just like earlier at the be well, not beginning of this video, but the beginning of the series section. Next, you might be asked to find the radius of convergence and interval of convergence, and honestly, you probably will be, because this tells you where that this is a valid representation for the function, because it won't be valid necessarily everywhere. It will just be only valid at a certain interval, and you do that the same as we just did a little bit ago when we did the ratio test to do that. So ultimately, that's what the process is for a Taylor or Maclaurin series. They're the exact same, except for if it tells you Maclaurin series, then you're going to know that A is 0. That's the only difference. Um, so the thing about these is you're going to just want to do practice, as much practice as you can. All right, now we're not even done because there's a lot more to talk about with Taylor series. So note, sometimes only taking the derivatives won't help you see a pattern. Remember, plugging in A may help. I said that. Sometimes you can just take the derivatives and you can find the pattern. Other times you're like for example, if it was sine, if you took the derivatives, you'll just be like, okay, this is stupid because if you take the derivatives, it's going to be cosine, negative sine, negative cosine, and it would just be like that, and you'll be like, that doesn't seem like a pattern. So sometimes it won't help, especially for the trig ones. But then you're like, okay, plug in A, and then for the trig ones, you'll generally get a pattern that's more like 0, 1, 0, negative 1, 0, 1, 0, negative 1. And that is a pattern you were only able to see that by plugging it in. So that's why sometimes you have to do that. And that's where it's actually harder for the trig ones. They're right here, and you might just consider memorizing this table, or you might be asked to derive it yourself. So you still should know how to do it, but these are the actual ones that are good to know. But nevertheless, uh for that ones like that, you'll find out that using a 2n plus or minus 1, it should say plus or minus 1, will help something always be odd. Think about that. Any n that you plug into that expression would always be odd because 2n by itself will always be even because like 2 times 1, even. 2 times 2, even. 2 times 3, even. But if you add or subtract 1 to that, it will always be odd. So this is a useful expression if you want it to always be odd, and 2n is for if you want it to always be even, and negative 1 to the n is if you notice that it always alternates. So that's what it's like. Because if you notice, like, okay, um, 1, negative 1, that's always odd numbers, right? So you might want that's where this comes from um, for some of these because it's telling you, all right, each odd one um, is only what we're doing because the even derivatives are always 0, or it's reversed. So that, see sign right here, it's 2n plus 1. Where that comes from is like it's all the all of the even derivatives are 0 for sine, but the odd ones actually have numbers and they're these. But then cosine, since cosine's just a little bit different than sine, just off by 1, instead it's the even derivatives that end up being uh not 0. The other ones are 0. So that's how that works. Um, like I said, it may be useful to memorize these just for guidance if you're ever asked to derive them. And actually, I would say you would want to memorize these that because we'll talk about in a second that we sometimes have to do similar use these to help us find the Taylor series of a similar one. So like sine of 2x or something like that. Like, oh, well, if we know sine of x, then that makes it pretty easy because all you have to do is multiply each of the terms by 2. It's not actually that hard. Just you do replace x with the thing that's beside. So, okay, instead of x, 2x. Instead of x, 2x for all of them. Um, Manipulate series to look like one of these with algebra. See, these are our friends right here. These will help us. And we actually already have known this one. I already said that. 1 over 1 minus x is just x to the n. That's like a really good one to know. And these have different radii of convergence, and you would find these using the ratio test if you wanted to, but these are what they are. And you might be thinking, why would the radius be infinity? Well, if you're doing the ratio test and when you take the limit, it ends up being 0, everything cancels out because if you multiply something by 0, it goes away. And if the limit goes to 0, then that means we have a radius of convergence of infinity. So that's basically the idea here. It's like, hopefully, almost always, you'll never get a question that asks you to find Taylor series unless it looks like one of these. Um, like that's really what's going to happen. So make use of that. All right, the next thing we're going to talk about with this is Taylor polynomials. So what the heck is a Taylor polynomial? You might be like, huh? Well, sometimes the truth is we are not always even able to uh, find an actual Taylor series representation because it's just too stupid. I mean, there's just not enough good patterns, and it doesn't look like one of these. It's like, hey, So instead, we're like, all right, Taylor polynomial. That means we're just adding a few of the derivatives, and we're going to say, good enough. So this is just an approximation. So if you're saying find the fourth degree Taylor polynomial, you're like, okay, well, we'll just do 4 derivatives and add them together, and good enough. That's probably close enough to what we want. That's what we're doing for a Taylor polynomial. So honestly, it's pretty much easier than finding a Taylor series. So, like I said, it's just impossible sometimes to actually find a Taylor series. That's just the real world. Some of them just the patterns are just not easy to find in the derivatives. So we can use this to approximate values, like for example, e squared, ln 1 of 1, or even pi. You could use it to um, find values of pi even. Now, obviously, e squared you could actually just find the Taylor series for that because the e to the x one is really easy, but but other times you just can't. So what are the steps for finding the nth degree Taylor polynomial? Now, what do I mean by nth degree? In case you don't know, I just mean they'll just say first degree, second degree, third degree, fourth degree, if whatever they say. So you take as many derivatives as it says, like whatever the number is, th, um, and then you plug in c to your derivatives. So you basically um well, actually, that's a little bit different. Like, if you're actually trying to find a value, you would do number two. If you're just asked to find just expanded polynomial, you don't actually have to do that. You basically just add the derivatives. But if you're actually trying to find something like e squared, you basically plug something into your derivative that you know the value of that's close um to the thing that you're having issue with. So so basically for e squared the two is the problem, right? Like we don't know what e squared is, but we at least know what e to the one is. So you just plug that in, and you plug those into this general form, and you stop at the nth term, and you plug in what you want to find. So you just add as many of these terms in the polynomial. That's what a polynomial is, as many as you wanted to find. And then later, once you get that form, you can plug in e squared to it or whatever you're trying to do. So this will make more sense when we look at examples, but this is basically what we're doing. So bottom line, what these Taylor polynomials are doing is they're basically like, you can think of it visually like on a graph, like we're trying to estimate a certain point. We'll just say, okay, you know, the slope of it's probably going to give us, say, an approximation. The slope of that slope even better. The slope of that slope even better. So basically, that the more things you add to the Taylor polynomial, the more accurate it will be. Because if you did, okay, let's just do infinity of these, well, then that's what the Taylor series is. And the point of why we don't always just do a Taylor series is because it's not always easy or even possible to find the Taylor series representation, since the patterns may just be so obscure. But that's what we're looking at right here. A couple concepts. And the thing about these two that have the purple background is that they're not as important to know, but they definitely can still show up on any exam you might have. And in the first place, the course that I'm going over may not completely align with what you're doing, but it should from pretty much every Calculus 2 course. But what are parametric equations? So this is really just completely different than what we were just talking about with series and stuff. Now we're just, I mean, it's completely different. So you don't even need to consider that right now. For parametric equations, basically the only equations that we've ever really seen, you've probably seen any equation that might be like y equals something, and then it will just have like x, or even possibly sometimes you might see something like x equals y squared. You know, you could get something like that, which you might consider like an implicit equation. But parametric equations are going to be equations. I really should have an example on here. So, all right, that's a little better right there. So that's what it's going to look like. It's going to be like, oh, two equations, one for x, one for y, and they have t's in them. Now, what the heck does this mean? Well, parametric equations are going to tell us more than just normal ones would necessarily, because basically what this is going to help us know is time, like at what point in time are we at this spot? And also it can tell us the direction. So we actually have movement now along the curve. So it's like you can almost imagine our graphs as being roads. It's like you're going driving down the line or the curve. Now, it's still going to have when we're graphing these, it's still going to have x and y as our axes. But what we're going to talk about as our last concept in this video, polar coordinate system, that will be different. But right now we're still with X and Y. So if you're asked to graph something like this, the there's pretty much two ways that you can do this. The first is you can come up with a few points. So you can say, okay, well, this is our interval 3. It's our interval of t, -3 to +3. So you would basically just say, okay, plug in -3 to both of these, -2, -1, 0, any points that you want, as many as you want. You could graph it like that because what this is going to actually say is that the graph is actually not going to be, going on forever to infinity or negative infinity. It's just going to go for those points. But keep in mind, these are not the x or y points. You find those by plugging it into here. to both of those. So we can do that, and then another thing that you can do is say, okay, well, if we're solving for t, like in this case, we could say, all right, t equals y plus 2, and then just plug in y plus 2 right there. That's another thing you could do, but it doesn't always work. But um, and then we also need, once we do that, we need to show the direction, and basically, you can look at the interval sometimes, or you can really just plug in points in the middle, and um, in this case, we would know, okay, starting wh wherever the coordinates were for this is going to be the first, coordinates for that is going to be the last. So that would tell you the direction. And you usually mark that um, like this. So if this is what it ended up looking like, you might do like something like this to show, okay, that's the direction it's moving. This is supposed to be review. That's why I'm kind of going it over pretty briefly. Remember, there will be examples in a different video. Now, there's more things that I'm going to talk about, and like I've said before, I'm going in more depth for some of these things in this video just because I don't have separate videos for these like I do for some of the other stuff. So that's why I have some separate slides for types of problems that you might see. You might get a question that says, find the tangent line at t equals something like 3, 4, whatever the number is, for the two equations. So it will say, find the tangent line at that point. And a tangent line is like any line, the only way you would find it is you need y equals mx plus b. You would need to figure out those things, but really it would be easier to use the point slope formula, and then we can just change it to that. So first, let's find that point. So you just plug in, like let's say it said t equals 3, you plug that into the two equations, and that gives you your coordinate, or basically one of the points for the point slope formula. Then define the slope. Remember, the slope is what we know. We can find that by doing the derivative. So we do dy divided by dx, or not divided by, sorry, dy dx, sorry. And then the formula for that is actually going to be the derivative of the y equation divided by the derivative of the x equation. So if it was like these, derivative of that divided by derivative of that. And then plug in the t equals whatever to that for t. And then after you plug in that, the number that you get is your m. You plug that into this equation, and then you solve for y, and that gives you your equation. So, and solving for y is really easy because you just add that to the other side. All right, now you also might be asked to find all the places where there are horizontal or vertical tangent lines. Um, Now to find the horizontal tangent lines, you basically have to know that it's going to be where dy dt, or the derivative of the y equation, equals 0. And only that. So that means that the x one is not equal to 0. If they're that's you're going to see, and then for vertical, it's the opposite. Then where the x one equals 0, the derivative of the x equation, where it equals 0 only. That means that the y one won't equal 0. If they both equal to 0, then that's a completely different thing that we don't talk about right now, or not even in this course, I mean. So the steps for doing that, simply just take the derivative of the y equation for this part, set it equal to 0, and then solve for t. Then find the x and y points for those t's. So let's say we did that, and okay, -2 and 2 were the t values that we got. You plug in -1 and -2 to the x and y equations, and that gives you the x and y points where there's horizontal tangents. Now, the vertical tangents is really just the same thing, except for you do the derivative of the x equation. You might also be asked to find the second derivative, hopefully not the third, but if you were doing that, it's not actually exactly how you would think. It's not just, okay, take the derivative using uh using this equation and then do it again. There's actually something different. You'll have to use the quotient rule once you do the first derivative, because the answer that you'll end up getting will be a fraction. And then you also have to divide by dx dt at the end. That's crucial, this right here. Whatever, after you take the second derivative using the quotient rule, you have to divide by that. And if you're wondering why, it's just a matter of we kind of changed which variable we're deriving or doing it with respect to. So you just if that doesn't make sense, it doesn't really matter. Just know that you have to divide by the derivative of the x equation at the end. The last thing for parametric equations that you might need to do for calculus 2 is find arc length, and that's this is the equation to remember. And you might be thinking, what's the deal with this? Alpha, beta, doesn't really matter. You could use A and B. It's just basically the way that we derive this. You don't you don't really need to know that. It doesn't matter. I'll just say that there is a reason behind it, but it doesn't matter. So just use alpha and beta when you're doing this. So you just set up this integral. So for this integral, you need to, okay, find what alpha and beta are. It's just going to be the interval that it tells you. So if it says like -3 to 3, then -3 and 3 are what it is. Now you take the derivatives of the x and y equations to find these two things, and you just plug it in, and then you use any integration techniques that you need to solve. There's only two possible ones, u sub or trig sub. Try to do u sub because trig sub takes a long time. So basically, try to adjust the equation in a certain way to where u sub would work, and that means maybe you can factor something out of the square root to where u sub would work. That's the thing, probably the key thing about Calculus 2, if you haven't realized by now, you sometimes have to change things to make it into something that you can do. So, and if that fails, then, try trig sub. All right, so we're finally on our last topic here, polar coordinates. So as I mentioned, please don't spend too much time on these two purple concepts. They're not quite as important, but you definitely still may see them. Um, so polar coordinates, what are these? So basically, all we've ever known for coordinates are what are called Cartesian, which is ordered pairs that are x and y. If you recall, polar coordinates are ones that have an ordered pair that can be r, theta. And r stands for radius, theta stands for angle, as you might expect. So the reason why we even have this is that there are definitely certain types of curves and graphs that cannot really be displayed easily by x and y. So, like, for example, spirals, circles, things that kind of look like flowers, interesting kind of looking graphs. So, for radius, I wanted to talk about for both of them actually, what it would mean if it's negative. And sorry that it's uppercase. I think that's something that it automatically does, but we usually display this as lowercase r. But negative r means 180 degrees in the other direction, reflected about the origin. So what I mean by this is if we're always going to have a radius like that. So r and then theta is going to be here. A negative r would be like this, just reflected 180 degrees. Negative angle just means you would go in the negative direction, which means clockwise, because clockwise is negative. And so that would really be the same angle value, but just negative. So how do you change between the points? You may be asked to switch the coordinates. So if we're starting with polar with the r and theta, and we want to get to the x and y, we can use these two equations. They can be derived, if you're wondering, by the Pythagorean theorem, or trig using the right triangle, but you don't really need to know that. You can just memorize these two. And here's where it will be really important to know your unit circle values. I had that somewhere earlier in the presentation, just a good table, but you would also just want to generally know things like what would sine of pi over 6 be? What would cosine of 5 pi over 6 be? Like things like that, random, you just would want to know. Um, so that's what you can use for that. And then to go the other way, it's the thing you're going to want to do first is, graph the point, graph the X and Y point so you at least know what quadrants it's in. Sorry. And then use this equation, r squared equals x squared plus y squared, to find r. So this will make more sense when we look at some examples. And you can also use the equation tangent of theta equals y over x to find theta. Now, when you're doing this, you'll find whatever you end up getting, it's like you'll end up with tan inverse tangent, basically. And you'll be thinking, well, there's multiple answers for this. You choose the theta that's going to be positive and in between 0 and 2 pi that's in the right quadrant, which is why you would want to do this yellow thing, graph. All right. Sometimes you also might need to change between equations. Typically, if you had to do this, you would only have to change from polar to Cartesian. You don't really have to do the other way. And it's also not always even possible to do it the other way. But anyways, use once again this statement that's true to manipulate the things you don't want. So you use this to get rid of the r and theta and then add in put in the x and y that you do want. Now, how do you graph polar equations? Well, first of all, let's just talk about, how we can have lines that are x equals something and y equals something. They're pretty much constant lines. Well, let's talk about what it means to just have equations that are r or theta. They just equal a number. Well, r just equaling a number, like if we had r equals 1 or something, that would mean that the radius is always 1 and the angle can be anything. And if we had the angle always equaling a certain number, then it would just mean the angle is always that and the radius could be anything. Now, the steps for graphing polar equations is you're going to first want to make a table of your R and theta values. So just basically how you might do for X and Y, all right, let me plug in thetas and see uh, or sorry, let me plug in, you just plug in certain values of the radius and see what angles you get and vice versa, depending on what your equation looked like. And then you use these two statements that we've already talked about to change it to Cartesian equation if you needed, as we just mentioned. And then a couple other things that you might need to do is to find the tangent line. You would use this equation that's really just similar to what we did for parametric equations. Same thing with the arc length. We would use that same formula. I'm just not going to really go through that here and there are other things that you may have to do that won't be covered by me in this case because that's just too much to talk about in this video. And it's not covered by the course that I follow. But that's it for polar coordinates. So the last thing I want to look at right here is just once again, we're going to just think about all these concepts. You want to ask yourself these questions before you look at the practice problems. Do you think you know how to do all these things? Like, let's just say, do you remember the basics of taking derivatives and integrals? All the different rules involved with that. Do you remember your unit circle? Do you remember, you know, basic U sub, finding the area between two curves, the three different ways that we might find volume, work, um, average value of function, the different integration techniques, which one to use when, the different ways to check if series converge or diverge, which one to use when. Of course, the Power series, Taylor and Maclaurin series. And then lastly, these two purple ones, as I mentioned, not quite as important, but you still would want to know the basics about parametric equations and polar coordinates. This is a whole lot of content, and I'm sorry that this video was this long, but I think I got a little rocky at the end, a little bit tired currently, but um, anyways, I hope this helped to some extent, and keep in mind, I'm gonna make a practice problem video soon, and the way that it's gonna work is if you comment that you'd like the link for it, then I'll send it out. Otherwise, it's just going to be uh, unlisted, but I will have that there if you want it. Thank you for watching.